First piece of my wonderful lecture is going to be gone. It's all John's fault. Okay. All right. So coming back to the lecture. So bisimulation is this thing that I can do whatever he does and he can do whatever I do. That's the notion of bisimulation. Now, is that the same as language equivalent? It's not. It's more. It's much stronger, and we'll see some example of that is the case. So now, if you have a deterministic machine, good news is that language equivalence and bisimulation is exactly the same, right? If the machines are non-deterministic, not true, and we'll see how that can be possible. Okay, so this is the equivalence between the state driving and the state tilted and straight, and so for every move that I do up there, I can do down here, and this state is equivalent to these two states, right? So I can indeed reduce the dimensions of the finite state machine without killing its behavior. Now, what is the difference between equivalence and refinement, right? So equivalence, as we said before, is that there is this notion that we can do the same thing. Now, when you have a refinement, what do you have in mind? So I have this thing, which is a specification, right? And a specification, in general, it tells me what I need to do, but it doesn't tell me things that I don't care about, right? So when I do an implementation, I may have to specify everything, right? So when I do that, what am I doing? Am I copying what this thing is telling me to do? I'm doing less, I'm doing more. What is it? I do more. No, I do less. Indeed. And that's a notion of refinement. Why do I do less? Because if I say the only thing I care is that I move straight, right? And I don't say which steps I'm going to take, it implies that if I do the long steps or the short steps, doesn't matter, right? When I implement the fact that I need to go from here to there, I need to decide what my stride is going to be, and that is my implementation, right? And so it's less, because the specification contains all the correct behaviors, and the refinement is picking one, right? The implementation is picking one. A refinement is a subset, okay? So it can still be many, right? So when you go in design, in general, you have a specification, then you do a first refinement, then a second, then a third, then a fourth, and then you get to implementation. And implementation, everything has to be decided. So the actual implementation is always deterministic, right? No matter what you do, it has to move in the physical space, right? So it has to be deterministic. And if it is not deterministic, it means that you don't want to represent a piece of the actual implementation. But the thing itself has got to be deterministic. The model may be non-deterministic. Okay. So two-state machines M1, M2 that are not equivalent may be related, and that's the relation that I was talking about, the containment, right? So my behaviors are all contained into the specification. So that's it. So M2 may be type compatible with M1 in that it can replace with M1 without causing a type conflict, which means that if my finite state machine has input-output spaces that are in the real space, right, in the real numbers, if I take the natural numbers, I have a refinement, because the natural numbers are a subset of the real numbers, so I'm okay, right? So I'm type refined. M2 may be a specialization of M1 in that it can produce only output sequences that M1 can produce, but not vice versa. As we said before, right? So the specification was saying go from here to there, but I'm taking a particular stride, so whatever I do is contained, is in their specification, but that specification does more. So that's what the specialization relation means. M2 may be a specialization of F1 in that at every reaction M2 can produce all the output values that M1 can produce. And that is meaning M1 simulates M2. So it can do everything that, can do exactly the thing that M1 can do. All right. Now, in all cases, if M1 is valid in a system, then so is M2. So I can replace it, right? and I'm not going to change substantially the behavior of the entire system. But the only thing that is matters in all these three relations that we saw there is what we mean by valid. So it's a type containment, is a behavior containment, is a reaction containment. So every time I have to specify what do I mean, what is my metric, right? So for example, have you ever asked, is Apple phone better than Samsung? You ask me, I would say Samsung anytime. But why? Because I don't care about Facebook or this kind of stuff, right? But I do care about, being robust and fast and blah, blah, open. And so for me, Samsung is better. You ask him and say, no, Apple is better. So the metric matters. Better per se doesn't mean anything. You have to define what is the space that you are going to use to measure things. All right, and this is an example of that. Now then, M2 for all these three things is a type containment, language containment, simulation containment, which means that the refinement notion is related to the particular measure that you are using to decide whether the two things are the same or not. Now, in general, we also say that M2 implements M1. So M1 is the more behavior-rich, is the specification, and M2 is a restricted version, but doesn't go out of the space of what M1 is requesting to do. So now the question is a refinement, and then you want to see whether a particular machine is a refinement of another one with respect to the type, and that is very simple. So M2 is a type refinement of M1 if, now this one is an actor model, so P1 are the values X and W that are at the input ports, and Q1 is a set of values that the output port can take, so X and W in P1, and in Q1 is Y. Now, the other machine that we want to compare with is as a less rich input state, if you like, input alphabet, and as a richer output alphabet. Now, can we say that this one is a type refinement of that one? Well, if you have a subset of the types in there, certainly true, right? Because I have fewer things, and the thing here is contained in there, so I'm okay. But how come that Q2 has to be larger than Q1? The reason being is that I want to make sure that whatever I put in here comes out that is accepted by the one above. And so on the output side, I can be richer than the output side over there, as long as the input type is contained in that input type as well. Okay. Now, let's go to the garage counter, and we know that this thing is redundant, so we can reduce it to a single state. That's okay. And we know that there are states 0, 1, 2, etc., and this, the states correspond to the output. There is a one-to-one correspondence between the output and the state, which is the counter, right, that goes up, and the number that is in the counter goes up. So the input ports are P up and down, with types V up and V down present or absent, and the output port Q is count, where the type V count is a natural number from 0 to M. Now the sequence of ups can be present, absent, present, absent, present, absent, and S down can be this sequence. And the count, according to these sequences of the two signals at the input, is absent, absent, 1, 0, 1, and so on. So this is the output that is produced by the sequence of inputs that I showed in the line before. Okay. So now type refinement. An example of why should I care about type refinement. So I have a garage counter that has a display that can take up to 99 numbers up to 99, right? So it counts 1, 2, 3 up to 99. And I have another garage counter that has 90 spaces. Now, since the space of the output in the natural numbers is contained in the space of natural numbers of the one before, we can say it's a type refinement, right? So every time I I have this type refinement, I know that I can substitute M2 for M1, except that it's not always okay to replace M1 with M2. When is that? Can you give me an example? It's simple, right? Right, exactly. So if I have 92 cars, then I'm dead, right? 92 spaces, not cars, 92 spaces. And I have a machine that goes up to 90, then what do I do when I have 91 cars, right? So my counter doesn't give me the right answer. And so I cannot use that counter to represent the behavior of the system. Okay. The counter machine above, like that one up to M, can indeed be replaced by this. We already saw that, right? So it's a compacted version of the finite state machines above. And by the way, this machine is completely, totally, absolutely equivalent to the one above. The only thing is that the input and the outputs are defined in different spaces, so that the state doesn't correspond anymore to the output. So it's a more compact machine. But if you look at the sequences of input and output, it's exactly the same. It doesn't change. So with respect to input and outputs, they are the same. So if we look at again, the simpler model, which is the your robot model, and we say, when is it okay to replace one machine with the other? We say that equivalence in general is language refinement for deterministic machine, and for non-deterministic machine is the concept of simulation. Okay, so that's when it's safe to replace one with the other. But remember, simulation is one directional. Language refinement also is one directional, but language equivalence is exactly, if A is a language equivalent to B, then I can interchange both of them. Doesn't matter. I can take A or I can take B. It's the same, right? If instead is a refinement, I cannot do that, right? I can substitute the richer machine with the Turkier machine, but not vice versa, right? Okay. And in case you have a non-deterministic machine, then the issue is that one non-deterministic machine may have many more behaviors than another machine according to the choice that you make. So I can match whatever it does, but it can, even though it looks like we can produce the same sequences, if I move first, he may not be able to follow. If he moves first, I can always follow, but not vice versa. And that's the reason why you say simulation. But is not the same, absolutely not the same as the notion of language equivalence. Now, how are we going to distinguish this thing? We're going to talk about execution trace. Now, behavior, we said before, is something that represents what is the impact of this machine on the environment. And so the execution trace means I have a sequence of inputs and the corresponding sequence of outputs. Right? This we call is a trace, right? So I give you a specific sequence, and you get specific pairs of input, state, and output. And this one is a trace, right? So the trace not only contains the information about the input and the output, contains also the information about the state, right? So it not only says, okay, I give out this thing, but it's also saying, well, I'm going from this step to this step to this step, and so on. So it contains more information than what we saw about the pair, input-output pair. Because now, for example, I can distinguish between the response of these two guys, right? Because now I have the states in it. And so he was in the stuttering state, you were in a different state. So the sequence of state is different, right? So that is the reason why traces, include another concept on the language that simply the input and the outputs. So a behavior of the of a state machine is actually the set of all possible traces, right? So everything that the machine can do. That's the behavior of the machine. Okay. So now language refinement then is say that language LM of a state machine M is a set of all behaviors. So everything that the machine can do, all the sequences of input and output that it can produce, that is what the language of a machine is. By the way, if any of you has done a little of language theory, I don't know how many of you in computer science have done that, but you know that there are certain languages that are accepted by a finite state machine, right? And so what does that mean, accepted? So, hello, which means that it can be produced, right? Any regular sequence of statements can be produced by a finite state machine, right? So it's a very well defined language is when this thing is true, and it's called regular language, right? So it's a nice language, right? All right. So the language we said is a set of all possible behaviors for type equivalent state machine M1 and M2. M2 is a language refinement of M1 if the language of M2 is contained in the language of M1, which means that I have fewer behaviors than the other guy, and my behaviors are contained in the behaviors of the bigger guy, right? And so that is a refinement. So I have less behaviors, but all my behaviors are contained in the previous one. So M2 can replace M1 if its observable I/O behavior is a subset of that of M1. Why do we talk about observable behaviors? Because if I care about what the finite state machine does to the environment, I have to look at what is observable, what comes out of that finite state machine. So whatever is not observable, whatever it doesn't come out, I don't know, so I don't care. That doesn't matter, with respect to what the system does. Now, if some of you has done some continuous stuff, right, continuous system theory, they know about this observability and controllability concept. Now, that is related to what I'm talking about here. So a system, x dot equal to f of x and u, and y equal to whatever g of x and u, then we say that the thing is observable if for every transition of this continuous system, I can have a complete observation of the state and of the input that has produced that particular output. So in that case, I know that nothing goes on inside the machine that I cannot see. Now, why should I care if there is something inside the machine and I can see it, right? If I can see it, it doesn't matter. In principle, yes, it doesn't matter, but there may be certain things that you have not contained in your model that may completely kill the system. So, for example, the unobservable part of your system can be unstable. So the thing blows up, right? And you don't see it, but it's blowing up, right? That's not good. Yes? Go ahead.
In this case, right, say in a system we are replacing M1 with M2, right?
Right.
What happens to all those
behaviors
which were in M1 but they are not in
right.
M2?
But this is, again, you can replace it in the sense that whatever the new system does was contained in the original system. So if if that is a specification, then you are refining the specification according to the refinement relation, then you can substitute it. But if you are interested in all the behavior of M1, then of course not. Right? So, and remember that this also makes sense, especially in the non-deterministic case, where the non-determinism in the specification, it means you don't give a damn, right? And that is the reason why we define this way, right? And remember again that everything that I don't say, right, is very good. So one of the things that we did a lot in the old times in logic design was to beg the designers, tell us what you don't care about, right? Because every time you say, this I don't give a damn, is great, because I can play with that thing, right? I can decide what I want to do in this thing, right? And so I can play in such a way that I reduce the size of the system, make it faster, whatever, because I have weird behaviors, but who cares, right? This behavior don't matter, right? And so the refinement contains only the baby, but I threw away all the dirty water, right? Okay. So this is the key. Okay. So we said before the language equivalent is not enough in general for non-deterministic machines. Only in that case, because otherwise it's perfectly fine. So how so? So we have this nice machine on the left, which is deterministic, and it says that if x is present, then it produces 0 and moves to b. Then if x comes again, I get 1 or I get 0. So if x is present, I get 1 or I get to 0 in these sequences. Now, this other machine, it says that under a particular input, I can go to 2 states, right? So f or h. And f can only produce a 1, and h can only produce a 0. Okay? So now, this one, if you put any kind of sequences of inputs, you get the same outputs. Doesn't matter. I mean, it's just absolutely the same. Yet, what can be a problem, right? So let's look at the behavior of this machine. So suppose that I take A and I go into B, and that's fine. And I'm going to go in the second machine. I move from E to F. Is a possible behavior. Now, the next behavior of my machine M1 is going to take the branch and is going to D, right? Outputting a 0. Now, in the machine to the right, if I'm in F, can I produce a 0? No. So, they are equivalent, but they are not. And so, how so? Because of a non-determinism, right? So I took in one case, one direction, the other case I took the other direction, okay? Now, if I revert the choices, if one machine is allowed to choose first, then I can show that I can match the behavior. If I revert the order of choice, I cannot get it, right? And so this means that one simulates the other, but not vice versa, right? And this is only true in the case of non-deterministic machine because of these choices, right, that I have, and the large set of behaviors that I have as well. So, however, even though these machines have exactly the same input-output behavior, there is a context which M1 is not a valid replacer for M2, which is the one that I just told you about. So, suppose that M1 is a specification. So, everything it does is okay. So, if I replace M1 with M2, I am okay, because any move that M2 can make is okay, but not vice versa, as we just did an example for. Conversely, suppose that M2 is a specification, everything it does is okay, but it's not okay to replace it with M1, because in state B, M1 is always capable of making a move that M2 cannot match. Right? And so in one way is okay, the other way I cannot. So it simulates in this way. It's not by simulation. Okay? It simulates only in one direction. Okay. Now, so is in some senses we are talking about a matching game, right? So you make the move, I match. You make the move, I match. You can so anything that you throw at me, I have an answer. Okay? So that's a game that we are going to play. And the simulation relation is that that relation that establishes what I should put in correspondence to make sure that these two machines can produce the same output no matter what I throw at them. So I have S1 is A, B, C, D. S2 is the state space of the machine M2, is E, F, G, H, I. Notice that S2 has one state more, but they still are output equivalent, so it doesn't matter if the states are same number or not. I can get a language equivalence even if I have different set of states. Now, I call a simulation relation the set of pairs of state S2 cross S1. And let's see how this set is built. Okay. So I start with E and A, right? So that's my first couple move. So on the machine M1, I'm in A, and on the machine M2, I am in E. So the beginning of the game. Let's the game begin. Okay. So now this pairing EA of initial condition, I'm going to collect, right? As a pair, one state in S1, one pair in S2, put it together. Now then, I can decide where I want to go as a next step, right? So M2, suppose that M2 moves first, is a game. So M2 moves first. And it goes to F. Now, M1 cannot go back to B. So the next, quote-unquote, pair in the simulation relation is going to be FB. Is where I end up in the two machines. I end up in here and end up in there. Now, first possibility. The second possibility, instead, is that I go in B, M1, but M2 goes in H. And so this is also a possible choices, so it's another potential element of a simulation relation in the sense that describes a different choice for the second machine. Okay, so I keep on building. Now, next step. Now, the next step, I'm going to C and G, because x1, so from F I go to G, so CG is okay. And then from B I go to D, then from H I go to I. So these pairs, GC and ID, are other elements of a simulation relation. So this is all pairing that I can imagine, right? So it's all the possible joint evolution of the two machines. Now, that set of pairing of states is called simulation relation, okay? Now, why should I care about simulation relation? Because the existence of such a set is I can analyze and guarantees me that one machine can simulate the other. Okay, so that is the algorithmic side of the thing. So since M1 simulates M2, M2 refines M1, M2 can replace M1, everything M1 is okay, so is M2. And so we say that this pairing of EAF, BHP, GC, ID is the simulation relation for the pair of machines, where M2 is the secondary machine, is the machine that I'm going to replace M1 with. So it goes in this direction. So a simulation relation exists because I always let M1 to make his first choice, and then M2 follows. Right? Now, formal definition of simulation, given M1, which is the set of state S1, the set of input I1, the set of output O1, and U1 is the next state relation. Why do I say next state relation, not function? Any idea? But why is it not a function? Exactly, because it's a non-deterministic machine. So the definition of function says that for a input value x, I have one and only one output. Right? That's a function. Right? The definition of function. The relation is that I have one input, I can have multiple outputs. Okay? And the elements of a relation then is that input with this output is one element, then this input with this output, second element, this input with this output, third element. Okay? So it's a set. Okay? All right. So that is the reason why we indicate with U1 and not with, for example, F1, which will be the function that given a set of inputs and given an input, a given a state gives me the next state and the output. Okay? So it's a relation. So it can be multiple. All right. So we say that M2 is a type refinement of M1. We know that. It has to be, otherwise it doesn't even make sense to ask the question if M1 simulates M2. If there is a relation, which is, of course, a subset of S2 cross S1, where S20 and S10, the initial states, of course, belong to this set, because remember that the simulation relation is a collection of the joint movement of the machine, right? So I have to start from somewhere. So that where I start is the initial condition, and the initial condition has to belong to that relation. So for all the pairs that are belonging to the simulation relation S, the following condition holds. For all the input in I2, and for all states S2 and output 2 that belong to the reaction set of S2 and I1, there must exist a pair of state and output that belongs to an X state relation, such that the pair S1 and S2, S'1 and S'2 belong to the relation, and the output set of machine 2 is contained in the output set of the machine 1. And that is the reason why one simulates the other. If it is equal, then they are equivalent. They are bisimilar, as we say. But in this particular case, they are not. So because O2 must be contained in O1. So it may not be that way. So this essentially says that everything that the machine 1 does, then S2 follows. And actually, it's all the way around. That everything that M2 does is contained in everything that M1 can do because of this relation. So any evolution of M2 is contained in M1. So, as we said before, a stronger notion of simulation is by simulation. And by simulation means if machine M2 simulates M1, M1 simulates M2. So, by simulation. Right? So, which means that I can, since we are playing a game, right? So, I'm player number 1, he's player number 2. Then the by simulation means I move first, he follows. But I can allow him to always move first, and I follow. Okay, so it's by simulation. Now, is by simulation the same as equivalence? It's not, and we'll see later on, right? Because this thing that we discuss is that I always move first, I am the master, or he always moves first, he is the master. What if he is the master for one step, and I'm the master for the next step? Okay, that is tricky, and in fact, you can have a bisimilar machine and yet not be the same as the that it doesn't produce the kind of things that we want. So it's possible to have two machines that simulate each other that are not bisimilar. So this one is M1 simulates M2 and vice versa, but they are not bisimilar in the sense that if I take this interleaved kind of game, then I can get different behaviors. So given M1 and M2, then we say that M1 is bisimilar to M2 if there exists a relation, simulation relation, where we start from the initial state S20 and S10, and for all pairs in S, the following condition holds. For all I and S prime 2 O2 in U2 of S2 I, there exists a pair of states and outputs that belongs to the next state function of S1 and I, so that the pair, the next state pair, belongs to S, and O2 is exactly identical to O1. Okay, so that is the difference, right? We had before that O2 was contained in O1. And vice versa. For all I in I and S prime 1 belonging to this, there exists an S prime 2 O2 in this, such that S prime 2 and S prime 1 belong to S, and the two output sets are equivalent. So I can revert, right? And if I can revert, nothing happens. Okay. Now, simulation and train containing. So if M1 simulates M2, then I'm sure that the output sequence is the same. Now, if I have a machine in such a way that the output is the same for both machines, I cannot say that they are in simulation relation. So, and this is due to the fact that when I move in the finite state machine, the sequence of output don't tell the entire story. Also, what happens to the state matters sometimes, and that is captured by simulation, but is not captured by the output equivalence. It's the pairing of the states that matters, right? So, and in some sense, is the same thing as if I put the famous curtain, right? The output equivalence, I don't care what this guy does, right? If a machine can compute, in a horrible space can be 2 gazillion machines, I don't see it, right? And the human answer like this, the machine takes time, stutters, and whatever, right? So that is the language equivalence. So they do exactly the same thing. Now, this simulation concept is that they are doing the same sequence. So it's that as if the machine is going through the same step that the human mind will follow. So this is much stronger, right? Because, for example, in chess, I don't know how many of you have followed the Big Blue game against the Karpov, right? The great champion of chess, right? So he always won, except that all of a sudden he never won anymore, right? He couldn't win anymore. Now, if you look at the process Karpov was following, was a very reasoned kind, based on experience, based on patterns, and all of that. The machine was doing all of that plus, right? Plus it was doing exhaustive check of moves, right? And so it was beating it. So it's different sequence of thoughts, different approach to solving a problem. So if we say that they always come to if we change the white with the black, you always produce the same thing. We can say that the two guys are producing the same output, but not the same sequence. The way in which they arrive to the conclusion is different. And so the simulation aspect of things is that I care about how do I get to the solution, and not only the fact that I have the same input-output answer. So in summary, what have we done? So we have defined type refinement, and so we say that M2 can replace M1 without provoking a clash of the input and output spaces. Well, that's really the basic stuff. I mean, it's really, it would be really stupid, quote unquote, to define two machines and implementation that are not type refinement one of each other. Now, the interesting thing is that, believe it or not, but a lot of mistakes are done on this thing. So, if you want to look around in the domain of big designs and what went wrong and so on, sometimes people mess up because they mess up the type. There is a particular case in point of the large design that will remain unnamed and costed about $200 million, in which, you know what they did? Is that they had a connection, a scheme, right, where the various components should be connected, and they are connected to the external pin. And guess what they did? They inverted two wires. Inverted, like this. So if you had the type checking, you would immediately see it, right? Oh my God, I inverted the wires, right? They didn't see it. And so to find that that was the case took a gazillion hours because it's a stupid mistake, right? And so sometimes a stupid mistake is much more difficult to find than a very complex mistake. A simple check will find the stupid mistake. So don't think I say this type refinement is totally stupid. Yes, it's totally stupid, except when a man is involved and he had too much to drink the night before and he switches the pins, right? So that's, or he was thinking about something else. Okay. M2 is a language refinement of M1. We say it is when the whatever M1 can do, and whatever M2 can do, then M1 follows. Now, M2 is a simulation refinement of M1 if at every reaction M2 can only produce outputs that M1 can produce, but M1 could do more. M2 is bisimilar to M1. It's at every transition, either machine can produce all the outputs that the other can produce. So the two outputs are exactly the same. The sequence is exactly the same. But there is also, remember, this equivalence also of the steps that the two machines are taking. So it's the output have to match the state in which they are produced. So in all cases, we say that M1 is a valid inner system, and so is M2. So this is the notion of refinement, where only the meaning of valid, what is valid, what we believe it's valid, varies. So we also say that M2 implements M1 in the sense that, again, the sequence of refinements is always followed when you do a design top-down, right? So you have a specification, go refinement, refine, 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 until you hit the bottom, okay? So we are way ahead of our time, so we have about 20 minutes of free time, so which is not bad. I see someone likes that. And so I'll open to questions for another 5 minutes, and then I'll let you go and have a nice lunch. Yes?
So, suppose we have two machines that produce, say, periodic output.
Yes.
Say, sine wave, both of them.
Yeah.
Now, one machine produces sine wave shifted by pi.
Yes.
If we don't associate any timestamps, then the sequence of values produced by both the machines are same. So they are language equivalent.
Right.
Now, suppose we also associate timestamp to these values.
Yeah, then they're not.
Then they're not.
Exactly. So, but if you associate the timestamps, it depends. If you want to associate it in the sense that you want to produce as output the value associated with the time in which the value is produced, then they are not language equivalent.
They are not language.
But if I keep hidden the time tag and I look at the transition relation, then I may be able to see that they are not the same machine, right? Yeah. Because the state, it depends how I encode the states, yes.
But oscillation is algorithmic, right?
Excuse me? Now we are talking, say it again.
Generally, it's a sine wave. It has to start somewhere.
Yeah, it has, you have to start the vision. Yeah.
So if it's shifted, and you're talking about...
Yeah, they are not equivalent.
They're not equivalent.
Right, exactly. But the point is that output equivalence, yes, because the same sequence is produced. And the first step, if at the beginning, right, does nothing, then is a stuttering, and so the sequence is the same, because it doesn't have the notion of time, right? So the only thing, and this is doesn't have a notion of which states I went through to produce that output. So it's a matter how you model. In fact, I say, if you attach the tag of the reaction, then, of course, they are not equivalent, right? But if I look only at the output sequence, I may have the same. So suppose that the input is just tick, 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 is advancing by 1, right? And the first step is a stuttering step in machine 2, then is the same, right? Because the tag doesn't matter, right? It's the sequence that matters.
Right.
And so we say trace equivalent.
Any implementation of that system?
That's a different story. No, because if you take as a specification the input-output behavior, they will produce the same. It depends on what you define to be the specification. So if you say, so it's that you are making my points, right? You have to be careful about what you define. So your thing is right, his thing is right. It depends what you define the equivalence, so what you expose, right?
One more thing. So after we have associated a timestamp, a Boolean output of the machine equivalence is 0, that they are not equivalent.
Right.
But is there also any notion that you can compare how much same or how much different are the two machines?
Now, yes, but it's complicated, right? So, for example, in continuous time, when you have these kind of things, right? So, for example, hybrid systems, then there is the Skorohod equivalence, which says that a Skorohod metric, it says that, for example, two machines are quote-unquote related or doing the same or whatever, if the output you see is within a certain ball in time, right? So if you have a reaction which is delayed or anticipated, it doesn't matter, as long as it stays within a particular ball, right? And that's called the Skorohod metric. So you can say, for example, the two hybrid systems converge to a particular behavior. In the Skorohod metric means that they are delayed, right? There can be delays, right? But there is a metric, and what is a metric is a way of saying what is equivalent, right? And so it's quite interesting to find out that, for example, L2 metric, right? L2 metric is used to find out when, for example, if something converges. L2 means that the square root of the square of the components of the in the space, right? That is a metric, right? The size of the vector, right? And so if the difference between these two values go to 0, then you say that you are converging in the L2 norm. Is there another norm that you can define convergence? Yes, is L infinity. L infinity means that max difference goes to 0, right? Which is different than L2. Also because L infinity is non-continuous, L2 is continuous, and so on, right? So there are 1 gazillion different way of measuring things, right? And so, which is this point, right? So everything that you define to be your measure, there is a definitions and there are algorithms that are associated to the metric that you use. Right? And sometimes, actually, people play the following game in the sense that they want to prove something and they will invent a particular matrix or whatever that they need to prove what they need to prove on, right? So sometimes a matrix is invented after the fact, right? So I say, I believe that these two do the same, but they are different. So I have to invent a measure in such a way these two are the same, right? And this stuff is the same, right? It's exactly the same. You say, by God, this one is the same as that, so, but I have to find a metric that's telling me that. Right? And so you invent the metric later on. So, and the matrix, as we say before, can be many different things. So, for example, the equivalence, this matter up and down. Any other question? By the way, this is rather advanced stuff, right? So you will not find too much in your midterm or anything like that on this topic. But for graduate students, this is important, right? So in fact, one of my things, quote unquote, is that in the future we will be defining an additional course where more of the advanced stuff is going to go, and so the graduate students will only take that and will not take this class, because sometimes Graduate students may be bored to death, and sometimes the undergraduate students say, "My God, what is this crap that they are throwing at us?" Right? Not good, either way. So, but if the undergraduate students have complaints about, "I don't understand a thing," try to ask. I mean, it's not, I'll try to make it as intuitive as possible, walking around or jumping or doing something or picking up on the guys in the class. So don't be afraid. I'm not known to have eaten students who make horrible questions. Okay, any other question, comment? Okay, so class dismissed.